is Fedor Bogomolov, and this will be the second lecture of his mini course.
Good morning, everybody. So, yesterday I discussed the way to basically construct the special type of manifolds. Those by now have that named as hyperkahler compact manifold. And today I will describe some special type of construction, and one of the theorems about the lagrangian fibration. Okay, so I recall that so we have x, 2n, so this is complex hyperkahler manifold. So by Yau's theorem, so what it means, so it is, I would add simple sometimes. Simple. So what I mean by this is complex manifolds of complex dimensions. So 2n is complex dimension. It has a form 2-0 holomorphic non-degenerate holomorphic non-degenerate form. It is unique, and simplicity means unique up to Kahler, and H1 is equal to 0, x equal to 0. I think that's it. So what we know in general. So
May I ask you a technical question?
Yes.
I'm always getting confused about equivalent definitions. There's one definition where lambda 2 plus bundle is trivial. Is this hyperkahler?
Sorry, lambda?
Lambda 2 plus bundle over manifold is trivial. Is that equivalent to hyperkahler? Because that's like the sphere bundle of that's supposed to be all complex structures.
Well, let's say this, how to say? I think yes, I can't say 100%, but I think yes, because what it means this bundle is trivial. And plus, there is also if you fix a class of metrics, yes?
Yeah.
If you fix a class of Kahler metrics, then you have what is sphere. Yeah, a sphere bond and the sphere bond.
A trivial sphere bond.
It's trivial sphere bond because there are two parts. You have a sphere bond with several sections, which are not intersecting. So there is essentially the action of SP, kind of SP2, I think. So in which acts in four-dimensional space, rotation. So okay. So since the question arises, maybe I would say a few words. So this manifold. So this properties are kind of follow from relative. So this is just so the existence of such forms means just that there is this SP2L structure. So local coordinates which agree via SP2LC, via kind of algebra, in Hamiltonian algebra. Yeah. So this is SP is one of the few Lie groups which leads to an infinite dimensional local algebra of vector fields. So therefore, if we have a smaller group, like a SO for example here, then we are bounded to locally homogeneous spaces. So that's a standard Cartan classification. There are very few kind of infinite structures. Infinite, I mean coordinates are not prescribed out of finite dimensional space, so which can appear. It's pseudo-group structures. So there is SP, SL, and basically that's it, or products. Very few. been said. So there are a few exceptions. Okay, so now what means, so now, in addition, if X is scalar, but this is an addition. So this appears much more often on complex varieties, and there are examples of varieties which don't have Kerr structure. However, if you have Kerr structure, there is Yau's theorem, by Yau's theorem. There is a metric, there is a Kerr metric, so each class of Kerr metrics contains a standard metric G, Yau metric, with the property that G, let's say the corresponding form, yeah, okay, let's call the form G cross G bar is equal to W 0 cross W bar. So actually, you see it on the caramel, on the, I would say, in much higher dimension for the volume. So the volume of G is the same as the volume here, and hence, but because of that, you can do the following. I hope I'm correct with that, but you can do the following. You can organize new structures by adding. So you have A, B, and then G, C, W bar, and write equation equal to 0. And this gives something A square plus B square plus C square equal to 1. So constant. You look at constant, square is 0, but then you're getting something like that. So that's how you're getting sphere of deformation. So any element with this property, in fact, provides another structure. So there is this there are these circles, so there are these spheres of deformations which corresponds to conic bound in parametrizing. So this is parametrizing quadric. So together is one, but this is a very, so first, this is a very strong theorem. The existence of such a metric is, how to say, that was a conjecture of Calabi, and it was proved after me by rather complicated. So Calabi proved some kind of local version. So he showed what is a local deformation, but to show that you can always get corresponding down at the global metric on X is this property. It was done by Yau, and therefore, so this class in some way is very simple in terms of coordinate. This is a metric, but practically, how to say, it's not so visible. I mean, to actually, so suppose you have coordinates here, Z1, Z2, how to write that? There are practically no formulas. Up to now, we know this, there is a theorem of existence, and hence in some direction, some kind of standard spheres, real conics inside the Q. We know what are the deformation up to that.
What's the difference between G and G hat?
Well, there is a metric. Metric is kind of symmetric, yes? So you see, metric is some Aij, so Pzi tensor Pzj, yeah? And I wrote it, it's some Aij, Pzi. So this is wedge, this is tensor.
Oh, I see.
Yeah, you see, metric is symmetric tensors, but because of the existence of J, we can kind of twist it and get a form, and vice versa. So 1-1 forms go to metric, and 1-1 metric, Hermitian metric defines their form. So that's what happens on complex metrics. I just but that's quite approximately. So therefore, this trivial, there are many such deformations. Yes.
Is W automatically closed or you have to require?
This is closed.
Yeah.
This is closed. Yeah, this